So hello everyone and welcome to another short session about a project I'm working on. It's a video game, currently without the name, but it's supposed to be a 3D adventure with some puzzles included. Basically, I've decided to do some overview of the rendering pipeline I've implemented for this game. And just for a brief context, this is the game running in edit mode. I can just select things and move them around and stuff like that. I can do undo and so on. And maybe I can show you the game in a gameplay mode. So I can just walk through, interact with things, turn on the light, maybe go here and turn on the light also here. And now go to the kitchen. So basically this is it. For the rendering, I'm using Vulkan API. Currently it's running on Windows, but I have also a port of this game for Linux. But there are some issues and I mainly maintain the Windows version. Yeah, so it's pretty common Vulkan pipeline, I would say. There is nothing really special. Maybe I can show you some rendering modes. This is the lightning, including the GI. This is just the GI, diffuse color, screen space, ambient occlusion, and I'm not sure if there is anything more interesting. Yeah, this is the light distribution. I will actually explain each step individually later. I'm currently using the forward pipeline. There is also deferred implementation. The deferred one was actually the first I made, but recently I've re-implemented all that stuff to make it forward. Because I want to use multisampling, and you can do multisampling with a deferred renderer, but there might be some issues with frame buffers because you have basically multisampled versions, and that might be expensive on some hardware. What is interesting is that I'm using ray traced GI, so I can maybe give you more details a bit later in this presentation. There are also reflection probes. These are basically capturing the surrounding environment into the cube map, and later this cube map is used to generate reflections. I'm not sure if you can see it, but there is something reflected in a screen of the TV, also on Windows. You can also see my pretty cool rain shader. I can actually hide it. And this is the window without the glass, so all the rain is happening inside the shader of the glass. Same thing here. Maybe there will be some cool reflections in a kitchen. There's something you can see on the surface of the fridge. I have a game running in a Ensite, so we can actually capture the frame and go through it step by step. I've also prepared this little presentation or graph of the render pipeline. So let's begin. The first thing here is a prepass, where I actually draw all the geometry called for a current frame. In this case, all the stuff you can see on the screen is rendered, but I'm rendering just the depth information and normal map. So maybe take a look here. I'm not sure if I will be able to find it, but here we have prepass. And in the prepass, probably resolve. Resolve would be the best. Take a look at this dispatch. So this one is a for normal. And I should have another one. This one is for depth buffer. After the depth and normals are rendered into two separate frame buffers, I will actually resolve them because these two are rendered in a multisample. So I'm using, I guess, 4x multisampling for these two. So I need to resolve them, meaning basically combine all samples captured for each pixel into one pixel. So it's later easier to manipulate with them. And I also create a downscaled version for some later usage because in some cases you don't need like the full resolution of the frame. The half resolution is just enough, and it might be also faster for some effects I do later in a pipeline. After that, I'm capturing decals. I'm not sure if there are any decals in this frame, but maybe there will be. Let's take a look. Fragment shader, or it's yeah, this one. Maybe, yeah. So I have like two decals in this frame. Let's resume and take a look. I can change selection to decals, and we have two or maybe three decals right now visible in this frame. And these are just, I'm not sure if you can see it, but there is like a dust or some dirt on a floor. Let me zoom in a bit. Yeah, this one is not that much visible, but anyways, capture the frame again. So let me find decals. It's in the prepass, decals. And normalize. So this is just a simple texture buffer. It's RGB, and I'm just capturing the albedo value of each decal projected on a surface, and that is used later for the final render pass where actually the whole scene is composed. So what's next? After decals, I will capture the light information. That one I can show here too. We have a dispatch for this, and I think this one. Yeah, it's looked a bit messy, but what it actually contains is for each pixel I have stored in RGB and also alpha. I have stored ID of light used to lit this pixel. So this information can be later used, for example, for shadow sampling or for the final rendering, when you can pick just the lights you need and you don't have to go through all lights you have in the scene. So this way I can actually effectively call just the necessary lighting information I need for each individual pixel. Or maybe what is more precise is to say that it's for 4 pixels on the screen. Each pixel here represents like a 4 pixel chunk because this texture is actually the half size. So this is the lighting information. I also use this to analyze the frame, so I know which lights and what is the distribution of the light in the current frame. I can say like there is probably light with ID 6, which you can see in our channel, and that has like a pretty much all the screen covered. So this light will later receive like the more precise shadow map. Okay, let's go to the next stage. So next thing I do is screen space ambient occlusion. Let's take a look. It's a simple horizon-based ambient occlusion, nothing special here. Let's take a look at the output map. So again, it's half size of the screen of the frame buffer, and this is noisy information captured for current frame, and I think there should be also denoising pass. So this is how it looks like after denoising. We still have a bit noise here. Maybe this can be improved in the future. Okay, what's next? Then we are capturing shadows. I'm using like a regular shadow maps. There is just one trick, which I can show you here. Shadow capture. Yeah, the shadow sampling is actually split into two parts. In the first part, I'm basically rendering the whole scene from the point of each light, and I'm using this light information texture to actually pick only those lights which are currently visible in a frame. So I don't know, in this case it will be probably like 3 or 4 lights for this frame. So I render basically the visible part for each light into separate texture or into separate shadow map, and each let me focus here. There will be quite a lot of dispatches or draw calls. Yeah, that's a lot. I just want to jump to the end somewhere so I can see the final shadow map. So I'm using a single texture for all shadows in a scene, and based on a light information I have from current frame, this one, I can actually pick the resolution needed to have like a fine enough detailed shadows for each light. So this is probably for the directional light. It's a moonlight in this scene. So it received like the biggest texture because it covers the biggest part of the current frame. Then I have this spotlight. There is another spotlight for the lamp in the corner. This is in a corridor. This light is probably leaking through the wall, so it's captured too. What's the next? This is another light from the same corridor, and I'm not sure why it's here. Maybe it's from the last frame, I don't know. Yeah, that's probably from the last frame. And this is from the last frame too. So I guess I'm using just the 3, or yeah, probably just the 3 textures for this frame. So each of these 3 lights has assigned this shadow map. And next step of shadow capturing is the sampling of shadows. So in this stage, I will basically take all those shadow maps. I will take also the light information map, this one. And for each pixel in this map, I will calculate the shadow. It's again a bit messy, but what it means is that for light in a R channel, I'm getting shadow here, and I'm getting no shadow for this area. And these are like combinations of multiple lights being actually processed for these individual pixels on the screen. And this information is later used in a lightning pass to actually correctly generate the shadows. What's the next step? Okay, so next thing in the pipeline is global illumination. I'm currently using DDGI for this. That will be probably best to show in a game. So let me close this, and I can show GI probes like that. What it basically does, it captures for each of these probes the light information in a scene. I basically trace raycasts from each of these probes and accumulate the lighting information over the time. So it can be visible maybe like this. So when I disable the light, it will actually take, oh no, this one. Let's pick some better one, maybe this one. Yeah, when I disable the light, it will take some time for GI to adapt. So that's like a bit disadvantage of this technique, but yeah, I think in general it works pretty fine. You can also see when I turn the light on, it will take some time to actually adapt to the new lighting conditions. So without the GI, do I have a way to disable it? Yeah, this is without GI, and this is with GI included. I'm currently using ray tracing, like the hardware version on the RTX card. It works pretty well, but I guess for the final version of the game, I have to come with something which does not require the ray tracing. But it will be probably something very, very simple, like just the fallback version of this. I don't even know yet. Okay, let me capture the frame again, so we can take a look. This is the GI pass, so the first thing I do is basically ray tracing. I'm not sure if I can show any outputs of this, maybe here. Yeah, this is the output radiance. This is the texture containing, like, for each probe in the scene, it contains results of ray tracing for, I think it's, yeah, it's 128 directions in a one frame for each probe. After this pass, I'm fixing positions of probes used for GI. Actually, it could happen that some probe end up inside of the geometry, so we don't want that, and we want to push them out. So I'm basically using information captured from current ray trace data and shuffle them a bit to prevent any geometry collisions. After that, I'm updating the probe data. This one is for depth, this one is for irradiance. Nothing really interesting here. Maybe we can take a look. Yeah, this is the information captured for each probe. It's incoming light encoded into octahedral, and it's collected over the time, so it's a temporal solution. And I'm taking the current data and applying them to history data. So this is how the lookup texture for each probe looks like. So after that, I'm updating the borders of each captured probe data, because to sample them seamlessly, I need to introduce like small gaps between each cell, which is representing a single probe. And in this step, I'm basically filling that empty space. So the last step in a GI pass is actually using the captured data from light probes and getting light information for the GI for the current frame. So this is the result. Maybe I can do something like that so it's better visible. So the last thing here is the main forward pass, in which I'm actually taking all this information captured for the current frame and combining them all together into the final lit image of the scene. Let's take a look. Yeah, this one. There will be quite a lot of draw calls. So let's see the final image. Yeah, so this is the final lit image combining all the data together. So you can see we have like a directly lit part, we have shadow here, and we have also GI applied to these dark areas of the screen. Maybe let's resume and focus on some other place like that. Regarding reflection probes, they are not updated each frame. They are actually kind of baked, and I update them only in case the lighting condition in captured area changes dramatically, meaning when one of these two attached lights is turned on or off, the probe is dynamically updated, but otherwise it stays like this. Also, you can see the resolution is not that high. I can actually make it better, but in reality for this scene where I don't have any mirrors or things like that, this resolution is actually quite good enough. Okay, so after capturing the main pass or main lit frame, the bloom is applied. For that, let me go maybe somewhere here and capture the frame. So bloom is done in multiple steps. It's simple technique where you actually downscale the current frame into mid-map and then do upscaling back with a combination of each MIP level. Maybe I can see it somewhere here. Yeah, so this is for the light in a hallway. You can see I do downscale the whole MIP chain, and after that I go actually backwards and combine all those images back together to get this effect. And this is applied to the final render in a bloom apply step. So this is the input map, and apply it to the current frame. So you can see there's a bit of bloom around the light source here. And the last step is some post-processing done. There is not really that much interesting stuff going on. There is only some tone mapping for the lighting, and I can also decrease the saturation of the scene. I can do it from editor, I guess. So to get basically like a bit darker mood, I've made this level a bit desaturated, but I can change it from editor when I go for, I think it's in level options. Yeah, this one. I can change actually the tone mapping too, but let's do the saturation first. So this is like the full saturated color information for this scene. I use like 0.6 for the gameplay, and I also can change tone mapping. Let me hide the probes. And yeah. These are like various tone mapping filters I can use. So that's it for the rendering pipeline, and hopefully it was interesting, and see you later. Bye.